The third example is the same transient impedance amplifier, but this time it will be implemented as a two-stage amplifier. With the first stage will be a cascode stage, and the second stage a common drain stage, and this time we'll be driving a resistive load. So we have here, and yeah, we have the same specifications for the inputs, and we have the same gain specifications. It means that we will have also 100 kilo ohm resistance at the feedback, and we are going to do exactly the same things that we did before. So basically, we will have a cascode stage at the beginning, common drain, and connected to a feedback, and then we have our source here, and it will be like this. So this will be our signal path, and we have two ways of representing this. For the cascode, we have the following model that we found for the cascode. The common drain, we just have a MOS transistor connected like this, but we have also the possibility of changing it and put the individual transistor that form the cascode separately also. Yeah, this is probably more close to the reality because it has less assumptions. And also it is more similar to what we run in the cadence simulation. So our signal path for the simulation in cadence will look like this. For each of these hierarchies, each of these cells, it is a small signal model, so it is exactly as we have here. So again, we're going to assume that we have already finished our task for small signal tasks. We have checked the loop gain, rod locus, compensation, etc., and we are happy with the results. And then it is time to move to the biasing. So here is our setup. Very quickly, we check the simulation results that we have, and basically we have that the closed loop gain, we have a 100 kilo ohm resistance and this time we have much better loop gain. Obviously we have a two-stage amplifiers, and this is 99.5. The system, it is stabilized with this phantom zero capacitor that we have it there, and then yeah, it has actually not been done a really good job, so it is not in bother world positions, but it is stable, and we are going to assume for now that it is okay. So the example, it has been not prepared for compensation, but for biasing, that it is totally stable anyway. So we can see the rod locus here. The system, it is totally stable. Asymptotic gain, 100 kilo resistance. So we are happy with our signal path, and then we're going to replace all of these transistors with the self-biased transistors. So we have here, and that is how it looks our amplifier. Each transistor has been replaced, and then what we do here, it is basically we do exactly the same thing that we did before. We are going to run a check on these biased transistors, and at this point we can run the noise P0. We can run all kinds of simulations that we are interested with right now, including a DC sweep at the input, so that we can extract the linearity, the static non-linearity. And yeah, we have that the gain, it is 99.5 kilo. That is exactly the same. The position of the poles are approximately exactly the same as we saw before. So we need to check the we need to check the DC operating points. So let's check. So we check the voltages and outputs, DC operating points, and then we see that transistors are consuming they are exactly the same transistors, but just at the same currents to make this a little bit simpler. So these are 20 microamps following this transistor, this transistor, this transistor, and the VDS has been set to 400 millivolts for all transistors. So we can see that it is basically accomplishing this requirement. And now our task is basically to start moving all these sources. Okay, so we start moving the sources, and let's go step by step. The first is that BDS 0, we are going to push BDS 0 upwards. What is this? So this is BDS 0. I'm going to push this one in this direction and in this direction. So basically it is appearing now here and here. Second, I will transform the current source from IDS0 and IDS1, so I can merge these ones in one current source. So if you see the current source of 20 microamp coming from this point to this point, that it is basically the same at this point after I move this voltage source, and it is bringing a current also here, so I can merge these two currents in a single current. So I will just delete this one and put one current source flowing in this direction. Okay, so that is step number 2, that it is here. Number 3, VG0 has been pushed toward the left, so then we have this voltage source I will push in this direction and in this direction. Okay, so if I push in this direction, then we will appear here and here. Okay, and IDS2 has split in two sources. So IDS2 is at the output. This is transistor 2. So IDS2, then there is a current that flows from this point to this one. Then it can be split to a current flowing down here, and a current that flows up here. And then I delete this one here. And that is what we have here. Okay, then I have to check and simulate. I'm not going to do that now. I mean, you know, we have to check the DC operating point, and the AC simulation is exactly the same. And, then the next step, I will push the resulting voltage sources that are in the middle. So all this block that it is here, I will push in this direction and in this direction here. So we will move it to the drain and to the source, and then it will be moved also in this direction here. Okay, so when we do that, we will have that these voltage sources appear here, they appear here, and they appear here after I put these voltage sources there. Then I transform the current sources in the left to two sources connected to VDD. Okay, so now instead of having it connected only to this point, let's go back here. We change the green. So this current source that we have here, I will connect it to a node up to VDD, that it is here, and then I am bringing the same current source here connected here. Okay, and then I delete this one, so then I have only this one here. And think about this, this is already connected to BDD. And then I can delete a current source in parallel to voltage source. So if I have these voltage sources, the addition of these voltage sources here connected to this node, and at the same time I had a current source here that was going up, and then this current source, it is not anymore part of my circuit. Okay, it is basically independent. It is in parallel to a voltage source here, so I can just basically remove it. It is being, we can say that it's solved by the voltage source that it is on the right. So then I have to test it now to make sure that I didn't delete something by mistake. I didn't do a wrong assumption, and I continue with the next step. So I continue reducing. So I have the following. I have the following equivalent circuit here. I have a resistor in series with a voltage source, and generally speaking, making voltage sources, it is not easy. We should try to convert these to current sources, because then we can use current mirrors that are more simple to implement. So voltage drops and voltage sources are not very easy to implement. We can make these voltage drops, with we can probably make these voltage drops like this. So if there is some current flowing here, we can use a resistor to make the voltage drop, and for AC we can put a capacitor in parallel that short these two nodes, so it is a decoupling capacitor, so it short these nodes for AC, but probably that will be okay at board level, but integrated circuit we might try to avoid this implementation. So I'm going to convert this resistance and this voltage source in series to from a Thevenin to Norton, and that will basically produce this current source going up and the resistor that is basically the same. Then I will replace the voltage source in the right with VDD. Now at this point it is clear that the voltage source here, it is the largest. When I add these voltage sources, this will be the largest voltage that I have in my circuit, and this will be the minimum that I will need to put in VDD. So I can already connect this one, delete these ones, and connect this node to VDD. And what I'm doing is basically deleting this. I am letting floating the drain of this transistor that I have it here, the of M2. Okay, so I have connected this one to VDD, and the last thing I have done here, it is delete the current source in parallel to voltage source. Again, previously we have a current source here that it is in parallel to VDD. It is not part of my circuit anymore. So I can just delete this one, and okay, I am done with that step, and slowly we are eliminating a lot of these voltage and current sources. So the next step, it is this slide is repeated. So we go to the next one. So we go to this step. What we have is merge the current sources at the output. So we have a current facing up and a current face down. So we can just merge it and then we see that it is a current going down, and it has to be. We cannot really make a current going up like that. We will have to transform it, so this current it is facing down. So very good. Then we have we delete the voltage sources in the loop, and now we have to check if our loop can hold this DC biasing, if it is feasible for us. Okay, to use, and we just deleted a bunch of voltage sources that were there in the middle. Now at the input, we replace this. We did just the same that we did before. We replace the voltage source at the input with a capacitor. So that will be number 3. So check VDS voltage and modify voltage sources if needed. Now we have just deleted a bunch of voltage sources, and we need to check, and we are going to do that. This step we're going to do it in Cadence. And we did also something very important, is that the cell bias transistor has the bulk and the source circuit, but in reality for regular bulk transistors, you cannot really do that. Probably you can do that in the PMOS, but not in the NMOS. The NMOS have the bulk terminal connected to ground. So we do the connection to ground, and normally should not change the performance. If for some reason it changes, then there is something that has to be taken in consideration, because normally the circuit should not be so sensitive to that change. And then we check, and then now we are going to check this circuit in step 5 with Cadence. Let's see. Okay, so we're going to run ADL here. We deactivate the static gain sweep, because we have just broken the feedback at the input, so it doesn't make sense to run a DC sweep at the input anymore. And okay, so let's just run it. And we annotate the DC node voltages, we annotate the DC operating points, and let's plot also the AC here. So when we plot the AC, we see here that we have around 99.5. That is exactly what we simulated before, and then the bandwidth is also okay. So we are fine. And then let's take a look to the DC operating points. We can see that the feedback is working nicely. It is setting the voltage that is needed for the transistor to pass 20 microamp. I have that the feedback is actually doing its job, so it's not really a problem. Now here, for instance, I have the chance to move a little bit up or down these voltages. For instance, in this case is 300 millivolts. I can probably add some voltage here, and then move this node this node up or down if I want to do that. So I have this possibility. So this doesn't need to be perfect, as long as the transistors are in saturation. Remember that this voltage, the drain voltage, it is a floating node, so I have some freedom to move these voltages here. But in this case, I don't need to do that. So I'm happy with the result as it is now. Then I can go and implement the current sources and this voltage source that I have for the cascode. And here we can see the implementation of the DC voltage and current sources. So let's take a look what we have here. This is the same that we have discussed before. Input reference current of 1 micron, and we have current mirrors here and here and here. So we have this current mirror that it is basically creating the reference that I need in order to create both the voltage and the current source, the cascade output. But this one, it is also, I am using as a reference for this current mirror here. So I am taking directly from this node. For generating the voltage reference for the cascode device here, we have the voltage reference. I am using a diode in the same branch, so sometimes I can do like this. This is one alternative. For implementing the other voltage source that I need, I am basically using this diode, sizing of this diode that will allow me to generate the voltage that I want for this node. So think about this. The diode connected transistor have low impedance. It is 1/GM, so circuit is very suitable. And I have added also capacitor to filter the noise of this diode connected transistor, and also the high frequency noise that might come already in the current source. For the current mirror here, I am using this wide swing cascode, and then I need to generate the voltage for the gates, and I need to be using the same voltage here as a reference for the cascode device here, and it is pretty much related to this one. And when the sizes are sized with the same ratio, the voltage in this node and the voltage in this node will be the same, and that means that the current here and the current here will be exactly the same. And then that will allow me to have much savings on the voltage drop that it is here. So remember that if the transistors are in weak inversion, I need just around 100 millivolts. If the transistors are in strong inversion, I need to guarantee that VDS it is larger than VGS minus VT. So I can try to put the VDS of this transistor close to the minimum, and then let this voltage of the cascode to swing, to have a large swing. This solution here that it is implemented, it is much better than this one I discussed during the lecture here. This transistor here requires VGS, VDS will be all the time equal to VGS, and that it is always going to be much larger than VGS minus VT, VTH. So then you can see that it doesn't lead itself to a very large wide swing. Yeah. However, when we have transistors in weak inversion, it might be possible to have low values of voltages also here. An important detail here, the noise. Remember that the noise of the cascodes, they basically work like this. So we have the noise source of the cascode here, and at very low frequencies, and the assumption that we have large impedances here. Let's assume for a second that there is extremely large we can assume that it is infinite impedance here. This current does not doesn't have a path to flow in this direction to ground or to AC ground to VDD. So what is going to happen is that this current comes back here. So it goes like this and it comes back like this. So it doesn't really affect the voltage of the output node. The same with this cascode here. This cascode here will have a current noise here in this direction, and then this current will also be coming back here inside the transistor, so it's not going to affect the output voltage, and this happens at very low frequencies. So we can say that in a cascode device, put the cascode like this current comes back like this. So they are canceling both the source and at the drain, so there is no really effect on the output node. However, at very high frequencies there is a capacitance here to the bulk, and then some current start to passing in this direction, and then this cancellation doesn't work anymore. So when the frequencies start going up, there is going to be part of the current that flows through the load and then produce a noise at the output. So at very low frequencies the cascode do not contribute with noise, and then just when the frequencies start becoming very large, we see some noise contribution at high frequencies. Okay, so we're going to take a look. We're going to take a look to the simulation results for this circuit also, and let's see. We have the following circuit, and here is the complete implementation. Then let's open the simulation setup. And let's run the simulation, and then in this case there is more loop gain. This is a two-stage amplifier, so we can see that the amplifier approaches much better the nuller. So we see that it is 99.4, 99. Yeah, so it has a very little peak in here, but that's fine. So it really approaches much better than nuller, and high pass filtering due to the capacitor that we put here. So we have this high pass filtering behavior at the input, and at the output is limited in bandwidth. Let's take a look to the position of the poles and zeros, and see that the poles and zeros here, they are located in Butterworth positions. So the amplifier is completely stable. We can move the zeros here. We see that this one that we look here, it is a pole and zero that are superimposed, so they are canceling each other. And let's take a look to the noise now. The noise contribution, that it is very important for us. We go to results, print, noise summary, integrated noise voltage, and let's take the whole band from 0.01 to 100 megs. We include all types, and let's take the 10 first noise contributors. And we have the resistors, the source and the feedback at that are the largest contributors. Then it comes the resistor M0, as we expected. M0 is the input transistor. Then we have M6, and M6 it is the current mirror, the current mirror. And then we have M7. M7 it is transistor that it is the cascode for the current mirror that start to kick in noise. Also, it's 6% of the noise coming from this transistor, and 10% coming from the from this current source. Okay, so it is a little bit high. if we want, we can reduce the transconductance of this transistor. Let's annotate the operating point. We can try to reduce the transconductance of these transistors, and then the noise level of this transistor will go down. So just now is this one, it is 406. This is 21. So there might be opportunities to reduce the noise contribution of M6 and M7 by reducing their transconductance. That is by placing this transistor in a strong inversion. Then I reduce the amplification, the transconductance of these devices. And then the next one is M7. M7, it is located. Let's see. 7 is located 4. And 7 is the cascode, and then we talk about this one. M12 is here. They are becoming negligible. They are less than 1% noise contribution, the other ones. So just to show the effect of the high frequency noise, let's reduce the bandwidth, and then let's hit it again, and then we can see here that the noise contribution for a bandwidth of just 10 megahertz has reduced from 0.4 millivolts RMS to 0.2 millivolts RMS. So, and then the noise contribution of the cascodes have reduced a lot also. So this is, as I mentioned before, due to the capacitances to the substrate, this noise current of the cascode start to kick in at higher frequencies. But at low frequencies they really don't contribute with much noise. Something to think, because that might affect the way that we think of the sizing of these transistors. The size of the transistor will affect this capacitance to the substrate. The amplifier is stable, the gain is adequate, and the biasing, it is basically working. We see that we have around 20 microamp passing through the main branch of the amplifier. We have also 20 microamp passing through the second stage, first stage and second stage, and we see in the simulation results that our biasing is working properly.